I never know where to stand in the beginning. So now we're asked to integrate. Oh, I don't like that angle. Now we're asked to integrate x cubed plus x times e to the 3x with respect to x. So here again, you've got a product of unrelated functions. So these are the conditions where you should think about integrating by parts. And once more, the way that integration by parts works, it says that the integral of u dv is equal to u times v minus the integral of v du. Okay. So first step is decide what you want to let u equal, what you want to let dv equal. In this case, so both as far as, remember the two things I said before, you want u to be something that becomes simpler when you differentiate, ideally. You want dv to be something that's easy to integrate. Well, this gets simpler. I mean, simpler in terms of like lower power if you take a derivative. It's not exactly hard to integrate though either. So this one might be a little tougher to decide at the beginning what part you want to let u equal, what part you want to let dv equal. There's nothing wrong with just taking a stab at it. Let u equal this, let dv equal this, try it. If it looks like things are getting worse instead of better, if the integral v du turns out nastier than the original integral, then that means you should probably change it around and go back and switch up. Okay, I'm going to let u equal this part and dv is this part. So that might happen in the homework, and you should be ready, be willing to do that. So just to try it one way, see if it works. If it doesn't, then you go back. There's nothing wrong with that. In this case, we do want u to equal the algebraic expression here, x cubed plus x. So that means that du will be the derivative 3x squared plus 1 times dx. That leaves dv as e to the 3x. And again, if you're asking yourself, okay, well, how did you know that you wanted dv to be that? Why not make this u? Trial and error might be what it takes in the beginning. This has a certain pattern to it that you'll learn to recognize, and the more practice you do, the more you'll get a feel for, okay, so this looks, you'll have an instinct. You have to develop an instinct for these things. And so that's going to come from practice. I mean, that's the thing about Calculus 2. It requires practice. You can't cram for a Calculus 2 exam the way you could maybe cram for a Cal 1 exam. Okay, so to find v over here, we need to integrate e to the 3x. And this brings up a common integral that you're going to see throughout this chapter. So you'll find yourself integrating things of the form e to the kx, where k is some number. You'll integrate stuff like that all the time, e to the 7x, e to the negative x, that sort of thing. So I'd like to go ahead and develop a rule for that. So if we integrate this in terms of k, so we're just allowing k is any number, then the way that we should integrate this is let u equal the exponent. That's going to get confusing, isn't it? Because I've already let u equal something else. So instead, I'm going to call it t. Let t equal the exponent. So if t is equal to kx, then where k is some constant, then dt will be just that constant k times dx, which means dx will equal 1 over k times dt equals dx, right? If you divide both sides by k, let's say. Divide by k, divide by k. Okay, so if dx equals 1 over k times dt, then this integral becomes the integral of e to the t, and where dx is equal to 1 over k dt. So times 1 over k dt. So then we could take that 1 over k is just a constant coefficient, toss that out in front of the integral, and then we've got integral of e to the t dt. So the antiderivative, sorry I'm writing so much red here, doesn't show up as well, I think. antiderivative of e to the t is e to the t. So e to the t, which is kx, plus c. Okay, so here's a rule that you can use for the rest of this, well, for the rest of this class. Sorry, I can't get this lid on. So write this down. I'm going to write it here, but I'm going to have to erase it in a minute. Any integral of the form e to the kx dx, this will be 1 over k e to the kx. That's a good rule to just know. It's going to be a big time saver. So you don't have to write out this whole substitution every single time, because like I said, you're going to see stuff of this form a lot. E to the 3x, e to the x over 2. It's all e to the number times x. Similarly, so I'm not going to do the whole proof, but along the same lines, if you integrate sine of k times x, because this is another type of integral you'll see a lot in this chapter, same substitution would work. So you'd do t equals k times x, dt equals k times dx. So 1 over k dt equals dx. You wind up with a 1 over k out front. And then the regular antiderivative of sine, which is actually negative cosine. So negative 1 over k cosine of kx. I'm going to have to erase some here. Might as well get that negative lined up while I'm at it. So the integral of sine of any number times x is going to be negative 1 over k cosine of kx. And then by the exact same process, if we wanted to integrate cosine of a number times x, so cosine of 5x, the antiderivative is 1 over k sine of kx. So like I said, write down these rules here and feel free to use them, so you don't have to write out these u substitutions every time you encounter an integral of one of these forms, because like I said, you'll see it a lot. So what I'm saying is if you integrate sine of 2x now, by this rule, you can just straight away say, okay, sine of 2x, that's going to be negative 1 over 2 cosine of 2x, without showing supporting work. That's fair. Okay, so all of that to say, if we want to integrate e to the 3x, integral of e to the 3x by this rule here will be 1 over 3 e to the 3x. 1 over 3 e to the 3x. Okay. So these are going bye-bye. Hopefully you wrote them down. So now do the whole integration by parts formula. U times v minus integral of v du. So this is equal to u times v minus, I don't know why I wrote it here, I'm going to run out of room, integral of v times du. Okay, the thing to notice here, even if I simplify this, so I've been a big champion in the previous videos of make sure you simplify the integral that you end up with over here before you decide what else to do. This e to the 3x over 3, 1/3 times e to the 3x, I'm going to write that as e to the 3x over 3, just to condense this a bit. X cubed plus x minus, so the 1/3 can come out here. And now we're integrating e to the 3x times 3x squared plus 1. Okay. So then you pause and decide what to do here. Now this is another integration by parts integral. From here we would do integration by parts again. You can apply integration by parts multiple times. Just make sure that your integrals are going in the right direction. And by that I mean they're getting closer to being fully evaluated, which this one is. We had x cubed times the exponential expression. Now we have a quadratic times the exponential expression. Notice if we do the same kind of setup here, do this again. So u was the algebraic expression here. I'm going to stick with that plan. So I'm going to let u equal 3x squared plus 1. Then du will be 6x to the first. Derivative of 1 is 0, so that drops out, dx. Dv will be e to the 3x again. So v will be that same antiderivative, 1 over 3 to the 3x. Okay. And then we would do, okay, so u times v minus integral of v du. So what would that look like? We would still have this out front. So e to the 3x over 3 times x cubed plus x minus 1/3 times this integral here, which is where we were doing this integration by parts. So it'd be times u times v, so 1/3 e to the 3x, I'll write that as to save space, e to the 3x over 3 times this 3x squared plus 1 minus the integral of v du. So minus the integral of v times du. And with that one, notice we need to do integration by parts one more time. But if you do it one more time, you're going to have your answer. So if you're wondering, okay, yeah, I see this is going to work, but this is so time consuming and so easy to lose track of, like a coefficient. We've got a lot of coefficients floating around over here. There is a more straightforward way to write this out. It only works in certain scenarios, though. So let me show you the method, and then I'll tell you about when it works. So an alternative to doing this repeated integration by parts here, in this case, is to use what's called the tabular method. I want to keep this last line here, but I'm going to erase everything else because I want to show you that what we get matches. So instead of doing all of that, I'm going to use what's called the tabular method. Which is just shorthand for everything that we were just working on. So with the tabular method, we're going to make a little chart. First column is just a column of alternating signs. The second column is going to list u and its derivatives. The third column is going to list dv and its antiderivatives. Keeping in mind here that with integration by parts, integral of u dv is equal to u times v minus integral of v du, because I'm going to show you how this chart ties in with this formula we've been using. Okay, so we start by writing down some alternating signs. So just by that I just mean positive, negative, that sort of thing. U and its derivatives. So if we let u be this expression, which is how we integrated it a moment ago. So x cubed plus x. So here's one thing for when the tabular method works. Only when, well, only works well, or it's only straightforward, when the derivative of u is eventually 0. So it works well when you have an algebraic, sorry, I should get even more specific. When you have a polynomial as your u, so positive whole number powers of x, that's one indication this is a candidate for using the tabular method. Because the nice thing about polynomials is the derivative will eventually be 0. So if we start with u equal to this, then next line would be 3x squared plus 1. So the next line would be 6x to the first plus 0, so just 6x. So the next line would be 6, and then after that, 0. And then from then on out, du is going to be 0. Okay, now I guess I'm going to draw the lines across here. I was afraid it would make it look cluttered, but I want to be sure. Okay, you guys can see how this is supposed to line up. Okay, so then dv and its antiderivatives. So if this is dv, so dv is e to the 3x. We don't need to bother with the dx. Thankfully, we have that shortcut way of integrating this. So antiderivative is 1/3 e to the 3x. The antiderivative of that would be, so the 1/3 now is a constant coefficient, and then integrate e to the 3x, so that's going to be 1/3 e to the 3x. So you end up with 1/9, 1/9 e to the 3x. If we integrate it again, and you should keep integrating until you hit that row that has the 0 derivative. So we got to integrate 2 more times. So if we integrate again, we'll have 1/9 times 1/3, so 1/27 e to the 3x. If you integrate one more time, you'll have 1/27 times 1/3, which is 81. 1/81 e to the 3x. Okay, so we've got the chart filled out. So now we can use the chart to write out our antiderivative. When you're writing out the antiderivative, you go across and then down. Across and then down, like that. Writing out these products. So the antiderivative, I'm going to start by just describing it, will be positive 1, think of it that way, x cubed plus x times 1/3 e to the 3x. The reason you go across and down is because, so it has to do with this formula right here. So the integral of u dv is equal to u times v. Well, u, this was u, right? This was dv right here. We started by writing dv and its antiderivative. So this is v. So when we start out, we want u times v. So that's why you drop down a row. You're dropping down from dv to the antiderivative v. The reason you have the alternating signs here is because of the minus right here in your integration by parts formula. So when you apply integration by parts multiple times, every time the sign's going to change. You have a negative in front. It's going to change the sign on everything after. So that's why we have the plus minus in front. It's accounting for the minus and the fact that you change signs in that integration by parts formula. Okay, so first part of the antiderivative. Before I'm going to have to erase this to write the final answer. I want to just show you that it matches up with what we had so far before I abandoned this down here. So you'd have u, positive 1, u, which is x cubed plus x, times v, which is this e to the 3x over 3, or 1/3 e to the 3x, same thing, minus e to the 3x over 9, which is what we would have, right, when I multiply this out, times 3x squared plus 1. There it is. That would be our next term. So it's matching up with what we have here. I don't want this table to be magic. I want you to show you that it is actually equal to what you get if you went through the long drawn out process instead of the table. Okay, and then so on. But so at least the first couple of terms we can see agrees with what we had when we did this the long way. Okay, but so now using the table to write out our final answer. So we do want to write the actual answer to this problem. I better leave plenty of room. Okay, so like I said, positive x cubed plus x times, drop down a row, 1/3 e to the 3x, minus 3x squared plus 1 times, drop down a row, 1/9 e to the 3x, plus 6x times 1/27 e to the 3x, minus 6 times 1/81, so I'll just make it 6/81 e to the 3x, plus c. So notice if we kept going, everything else is going to be 0, because we'll have plus 0 times, who cares then? Because if it's times 0, we know it's 0. So the rest of it's all going to be 0. So this is your antiderivative. Yes, it could be cleaned up a little bit. I could simplify these fractions, but you've been through enough. Here's your antiderivative. You can do the simplifying on your own.